Hi everyone, welcome. Today we will continue to learn activation functions, part 2. By the end of this session, you will learn more nonlinear activation functions that are commonly used in neural networks. First, you are going to learn ReLU functions and its variations, such as leaky ReLU, parametric ReLU, and exponential linear unit, ELU. You need to know the difference among these models. Then I will introduce softmax function, which is a normalized exponential function that converts a set of real numbers into probabilities. You will also learn its relationship with the sigmoid function. Next, we will learn max-out function, which is recently proposed by Goodfellow. You need to know how ReLU and leaky ReLU are related with max-out. Finally, I will summarize the popular types of activation functions and when to use them. First, let's learn the ReLU function. ReLU stands for rectified linear unit. It is one of the most widely used nonlinear activation functions today, due to its simple definition. The ReLU function is defined to be the maximal value of 0 and its input. If the input value is positive, ReLU output the input value itself. If the input is negative, ReLU returns 0. It is a piecewise linear function, but globally, it is a nonlinear convex function. Based on its definition, ReLU can be regarded as an identity function with a zero threshold in its output. Due to its simple definition, ReLU neuron is easy to compute, and the neural network converges very quickly. When the input is positive, the slope of ReLU is constantly 1. Thus, the graph of its derivative function is a horizontal line for positive x. This implies that, for positive input, ReLU has no gradient vanishing problem, which is a main advantage over sigmoid and tangent h functions. However, when the input is negative, the output of ReLU is always 0, implying that its slope is constantly 1 as well. In this case, the zero gradient flowing through the ReLU neuron may cause the weights unchanged forever from that point on during the training. That is, the ReLU neuron becomes inactive and dies. The dead ReLU always outputs the same value for any input, so that it takes no role in discriminating between inputs. This is the main disadvantage of the ReLU function. In addition, ReLU is not a zero-centered function. Its output range is always non-negative. It is also worth noticing that ReLU is not differentiable at x equals 0. Graphically, we notice the ReLU graph is not smooth at the 0 point, leading to a jump at 0 in its derivative function. It can be seen from the ReLU graph. At the point x equals 0, the left-sided slope is 0, whereas the right-sided slope is 1. Since the left and right-sided slopes at 0 point are not equal, the derivative of ReLU at 0 point does not exist. To make ReLU work properly at this point, in practice, we often empirically define a value, neither 0, 1, or 1/2, for the derivative of ReLU at x equals 0. To overcome the limitations of ReLU, in what follows, I will introduce two variations of the ReLU function. One is leaky ReLU, which aims at addressing the dying ReLU problem. The other is exponential linear unit, ELU, to alleviate the indifferentiable problem of the ReLU function at the 0 point. Leaky ReLU is defined to be the maximal value of alpha times x and x, where alpha is a constant factor between 0 and 1. Unlike ReLU that zeroes out the negative inputs, leaky ReLU multiplies the negative inputs by a small constant alpha while keeping the positive input as is. Therefore, in the graph of the leaky ReLU function, there is a slight slope alpha for negative values. Accordingly, in the derivative of the ReLU graph for negative inputs, there is a horizontal line whose y-intercept is alpha. In leaky ReLU, the parameter alpha can be predefined by the user, whose value is often set between 0.01 and 0.3. Alternatively, we can also learn the value of alpha during the training to make the function better adapt to other parameters of the neural net, such as weights and bias. When alpha is learned automatically, this function is also known as parametric ReLU or p-ReLU. Both leaky ReLU and parametric ReLU have the advantages of no dying ReLU problem. They have no gradient vanishing problem as well, and easy to compute. However, leaky ReLU is not differentiable at x equals 0. Since its left and right derivatives at the 0 point are alpha and 1 respectively, they are not equal, leading to a corner point at x equals 0. Typically, we can define an output value for the derivative of leaky ReLU at a 0 point empirically, such as alpha 1 or alpha plus 1 over 2. To alleviate the indifferentiable problem of ReLU, exponential linear unit ELU function is introduced. ELU is also a piecewise function. The slope of the positive part of the function is 1, the same as ReLU. For the negative part, unlike ReLU and leaky ReLU using a linear function, ELU uses a nonlinear exponential curve, alpha times e to the x minus 1, where alpha is a user-specified hyperparameter between 0 and 1. When the input is very small and tends to minus infinity, we notice that this exponential term approaches 0. As a result, the negative part approaches minus alpha. This implies the horizontal line y equals minus alpha is the asymptote of the negative part. The concatenation of linear and nonlinear functions at x equals 0 makes ELU smoother at the 0 point than leaky ReLU. We can see from the graph of the derivative of ELU. When x is positive, its derivative is constantly 1. When x is negative, its derivative is an exponential curve, alpha times e to the x, whose y-intercept is alpha, unlike ReLU and leaky ReLU with 0 y-intercept. When alpha is set to 1, the derivative of ELU function is continuous, and thereby is differentiable at x equals 0. Moreover, similar to leaky ReLU, ELU has no dying ReLU problem and no gradient vanishing problem. During training, the convergence rate of ELU is faster than that of ReLU. However, the drawback of ELU is the computational efficiency. At testing time, due to the presence of the exponential function, ELU is much more time-consuming than leaky ReLU and ReLU. Next, we are going to learn softmax function. Unlike the aforementioned activation functions, whose input is a single value, softmax takes as input a vector of multiple real numbers. Softmax normalizes the n real numbers into a probability distribution, where each probability is proportional to the exponential of its input value. Therefore, softmax is also known as normalized exponential function. This is the mathematical definition of the softmax function. It is often used for multi-class classification tasks, where the output values are multiple. For example, suppose we have a neural network that classifies input data into one of the 4 classes. Before softmax is applied, the predicted value of each ith neuron at the green layer is Zi. They are stacked together in a column vector Z, which is the input of softmax. After applying softmax, we can get a normalized probability vector Y, whose ith entry yi is a rescaled real number between 0 and 1. Since the output is a probability distribution, the vector y satisfies each entry yi is between 0 and 1, and the sum of all yi in vector y equals 1. Next, I will give you an example to show how softmax works. Given the vector z, -3, 1, 0, 2, applying softmax to z, we want to get the output vector y. The computation of softmax can be tabularized as follows. We put all the values of vector z in the first column. In the second column, we apply the exponential function to each zi. For example, the value of z1 is -3. After exponential function is applied, it becomes e to the -3, which is 0.050. Similarly, we can calculate the other values. After that, we calculate the sum of the second column, which is 11.16. This is the normalized factor. Then, we divide each cell in the second column by this sum and get the following normalized value yi for each zi respectively. Stacking these yi into one column produces the output vector y of the softmax. We can readily verify that the sum of all yi in the last column is 1. Therefore, the result y is a probability distribution. It is important to note that the conventional approach to normalizing the given vector z is to divide each entry zi by its sum. Why not use this normalized formula here? The reason is that the value of zi can be positive or negative. If we directly add up all zi together, some negative and positive values would be cancelled out. In this example, we can see the sum of zi is 0, implying that we cannot use the sum 0 in the denominator. Instead, at the first step, we should apply the exponential function, which will map each zi to a positive region, e to the zi. After that, we can use this formula by replacing zi with exponential zi. This is exactly the same as the softmax function. Softmax is commonly used for multi-class classification. In fact, it is a generalization of the sigmoid function from 2 to n dimension. It is worth mentioning that softmax contains a special case of sigmoid when the number of classes n reduces to 2. Here is the proof. If we feed 2 input values, x and 0, into the softmax function, then it follows that y1 equals e to the x over e to the x plus 1. Multiplying by e to the minus x on both denominator and numerator produces the sigmoid function. Then we can get y2 equals 1 minus sigmoid function. The proof of this result provides a new mathematical insight on generating the sigmoid function. We can see from this red equation that sigmoid is the quotient of 2 functions, e to the x and e to the x plus 1. Let's depict these 2 functions in different colors. The red curve is e to the x, and the blue one is e to the x plus 1. We now squeeze both curves using the same ratio. We can see when the blue curve is squeezed into the horizontal line y equals 1, the red curve becomes the sigmoid function. This actually shows an alternative way of looking at the sigmoid function, which is the exponential normalization of e to the x and 1. The last activation function we are going to learn is max out. The max out function is proposed by Goodfellow in 2013. It is a piecewise linear function that returns the maximal value of the input data. Below is the mathematical definition of the max out function, which is the maximal value of w1 times x plus b1, w2 times x plus b2, and wk times x plus bk. Here, x is the input vector. wi and bi are the learned weights and buy-ins. K is the user-specified parameter, which is the number of linear pieces, or alpha feature maps. Let's take an example. Suppose we have three input numbers, x1, x2, and x3, denoted as three gray nodes, which makes a column vector x. The green node has a max out activation function. Suppose the given k is 2, meaning that users would like to use the max out function consisting of two piecewise linear functions to return the maximal value of the inputs. We can imagine there is an immediate hidden layer with two red nodes added between the input and output layers. The weighted sum of the three input gray nodes is respectively passed to each red node. Then, the maximal value of all the red nodes in this layer will be passed to the green node in the last layer, which is the output m2 of x of the max out function. To show how the output of max out is computed, let me give you a small example. We set k equals 2 for max out. Then, the max out function takes the following form, which is the maximal value of two piecewise linear functions, w1 times x plus b1 and w2 times x plus b2. This implies there are two red nodes in the immediate layer, whose immediate values are denoted as z1 and z2 respectively. Given the input values x1, x2, and x3, we are now ready to show how the output y is obtained. Firstly, we denote by w11, w21, and w31 the learned weights on three edges between all the gray nodes and the first red node. We put these weights together in a row vector w1. Similarly, we use w2 to denote the weights w21, w22, and w32 between three gray nodes and the second red node. Let x be a given input vector, which is a column x1, x2, and x3. We first compute z1, which corresponds to this part of the max out. It is the weighted sum of w1 times x plus b1. Substituting the learned values w1 and b1 into this formula yields the following result for z1. We next compute z2 in a similar way, which corresponds to this part of the max out. We can get the following result. Finally, in the last layer, we compute the output y, which is the maximal value of z1 and z2. This is exactly the result returned by max out. Now let's look at a concrete example where the input x and the learned weights and buy-ins are given as follows. Then, to obtain the result of max out, we write w1 as a row vector 1, 2, minus 1, and w2 as a row vector 0, 1, minus 2. The input x is a column vector 2, 1, 0. Then we compute z1, which is the weighted sum w1 times x plus b1. We plug in the concrete values into this formula and get z1 is 2. Similarly, we can get z2, which is 3. Finally, taking the maximal value of z1 and z2, we get the output y of max out, which is 3. It is important to note that max out is essentially a generalization of ReLU and leaky ReLU. We can see that when the number of linear pieces k equals 2, if the weight and bias of the first piece are set to 1 and 0, respectively, and their values of the second piece are set to both zeros, then the max out function reduces to the maximal value of x and 0, which becomes a ReLU function. When we set w1b1 to 1, 0 and w2b2 to alpha 0, then max out reduces to the leaky ReLU function. In addition to ReLU and leaky ReLU, if we set w1b1 to 1, 0 and w2b2 to minus 1, 0, then max out becomes the absolute function. As a result, we notice that ReLU, leaky ReLU, and absolute functions are special cases of max out. Thus, max out enjoys all the benefits of ReLU and leaky ReLU. When we increase the number of linear pieces k, then max out can approximate nonlinear functions in high accuracy. Here is an example of a quadratic function approximated by max out when k is set to 4. We use 4 linear pieces as an approximator. Each linear segment corresponds to an immediate hidden node. For example, the red line is associated with the red node. The yellow line corresponds to the yellow node. The green one is associated with the green node, and the purple one is associated with the purple node. After all the values of the hidden nodes are calculated, max out returns the maximal value of Zi as the final output. From this example, we can see the drawback of max out. When k is larger, despite its high accuracy, max out is computationally expensive, as it will generate k additional intermediate hidden nodes, which increases the number of parameters k times for each output. From this example, we notice that a max out unit can learn a piecewise linear function with up to k pieces. Due to the use of the max operator, the piecewise linear function generated by max out is a convex function. Therefore, a single max out neuron is good at approximating convex functions. However, if we want to approximate any continuous function, it is better to use 2 max out neurons. This is because, mathematically, it can be shown that any continuous function can be expressed by the difference of 2 convex functions. Thus, to emulate any continuous function, we can build the following neural network. We construct the first max-out neuron, Y1, using 4 pieces, and then build the second max-out neuron, Y2, with the same number of pieces. Since any continuous function y is expressible as y equals y1 minus y2, we add another layer to combine y1 and y2 together, whose edge weights are 1 and minus 1 respectively, such that their weighted sum is y1 minus y2. Before ending this session, let me summarize the common activation functions we have learned so far. The binary step function returns a binary value and is often used as a binary classifier. It is not recommended to use in hidden layers, as its gradient is 0. It is often used in perceptron and NP neuron for binary classification. Linear function is often used in linear regression. However, its gradient is a constant value independent of the input data. Moreover, it is not used in hidden layers, because the linear combination of linear functions is another linear function, which will make all layers with linear activation functions collapsed into one layer. Sigmoid is a smooth nonlinear function. It is often used in logistic regression. However, it is costly to compute and has a vanishing gradient problem, and its range is not zero-centered. To fix this issue, tangent H is proposed, which is a rescaled version of sigmoid. Tangent H is zero-centered and is often used in recurrent neural network. However, its computation is rather costly as well. To reduce the computational cost, ReLU is introduced. It is a linear piecewise function. Due to its simplicity, ReLU is highly preferred in hidden layers for multilayered neural networks. However, it has the dying ReLU problem and is indifferentiable at 0 point. To address the dying ReLU problem, its variation, leaky ReLU, is devised. For negative part, leaky ReLU introduces a hyperparameter alpha, which is user-specified. If alpha is learned during the network training, this function is called parametric ReLU. However, both leaky ReLU and parametric ReLU are not differentiable at 0 point either. To make the piecewise activation function smoother at 0 point, another variation of ReLU, ELU, is proposed. It combines the nonlinear piece and linear piece in a unified manner. ELU has higher accuracy than ReLU, but it is more computationally expensive. Softmax is a normalized exponential function. It converts a set of numbers into probabilities, which is often used for multi-class classification problem for output normalization. Sigmoid function is a two-dimensional version of the softmax. Maxout is a modern activation function recently introduced by Goodfellow. It employs multiple piecewise linear convex function as an approximator. It covers ReLU, leaky ReLU as special cases. Maxout achieves higher accuracy, but its computation is rather cost-inhibitive. That's all for today's session. Thank you for your watching. Bye.